Hi there and welcome to Lab 7 of Biostats. So today we're going to be looking at the linear model and we're going to be using the donkey data. So you remember the linear model is a way that we can model the one variable, which is usually the outcome variable, in terms of one or more predictor variables, so that we can sort of predict what the outcome variable is given what we know about the other variables. So I'm going to run this code in this first block to produce this first plot here, okay, which is a plot of heart girth versus body weight. And just to describe a little bit of what's going on here, you'll notice that I'm using a subset command here to filter out the donkeys that have height less than 150, and that's because there was an outlier in this data that I don't think you've seen. So let's just have a look at that by doing a so if we look at height versus length, and if we have a look at that, then you can see that there's this outlier up here. So this is with all the data, and so we're removing, so we're only keeping anything with height less than 150, which is that line there. Okay, so if we redo that same plot, this time with the filtered data, just using the donkeys instead of all donkeys, then you can see that we filtered that out. Okay, and we're going to finish by doing looking at the heart girth. Okay, so we can see there's a clear increasing trend between heart girth and body weight. The trend is mostly a straight line, and the points cluster reasonably tightly around the trend. Okay, a linear model will make sense for these data. Okay, so next we're going to fit the linear model, and you remember from lecture 6 we did this right at the end. This is the code for doing it. So we use the LM function, which is short for linear model, and then we write a formula which specifies the formula for the linear model. So here we're having body weight in terms of, that's the little tilde, means in terms of heart girth, using the data from the donkeys data set. So when I run that, I get LM1 and a object up here, and then I can run the summary command on it, which gives me the summary information. And we're going to write some notes on this. So the first thing we note is we can write down what the formula is. So the equation that relates the heart girth, the body weight to the heart girth is body weight is going to be equal to minus 194.5. So that's the value for our estimate of what the intercept is, plus 2.83 times heart girth. Right, so the 2.83 is the thing that gets multiplied by heart girth. So let's sort of interpret this a little bit. For each 1 unit increase in heart girth, there'll be a 2.83. So the units are centimetres. 1 centimetre increase in heart girth, there'll be a 2.83 kilo increase in body weight. Okay, so that's what the 2.83 means. The minus 195, that's going to be the body weight of a donkey with heart girth 0. Right, so if you put heart girth equals 0 in this equation, you get 2.83 times 0, so minus 194.5 plus 0. So when the heart girth is 0, the body weight is minus 195 kilos, which is silly, right? And it's silly for two reasons. First of all, it's negative. That doesn't make any sense to have negative body weight. But also, you know, the heart girth is never going to be 0 centimetres, is it? Right? If you have a donkey, its heart girth will be some positive number, okay? And the reason this is silly is that the value for heart girth being 0 is so far out of the range of our data. If you actually look at our data, the smallest heart girth we have is 80. Right, so our data sort of starts at 80 and goes up from there. So anything, you know, the heart girth less than about 50 or so is going to be completely meaningless. right? Okay. Right, what about the p-value for the slope? Well, you remember from lecture 6, when we think about testing a hypothesis test for a linear model, what we're testing is there a relationship? So this is testing whether a straight line relationship between body weight and heart girth makes sense. Well, whether there is really. Okay, and if you think about it, if there was no relationship between body weight and heart girth, then we'd expect the slope to be 0. So essentially what this p-value is measuring is how often by chance would we get a slope larger than 0? In fact, how often would we get a slope as big as 2.83 just by chance? Okay, and you remember in lecture 6 we looked at that, right? We looked at the sort of set of slopes that we might expect from the data, given our sample size and the variation that we have in the data, and we saw that it was actually quite small. We'd expect it to be centered on 0 and maybe be up to sort of plus or minus 0.5 or so. But we got a very large one, 2.83, which is miles away from what we'd expect to happen due to the sampling process. So what we got from the sampling process in our sample is clearly not from a population where there's no relationship between heart girth and body weight. It's from some other population where there is a relationship. Okay, so that's why the p-value is so small. It's saying our data are super extreme. If it were to have come from a population where there was no relationship between body weight and heart girth, and because the p-value is so small, our conclusion would be there is a relationship between body weight and heart girth. Okay, so the p-value is really tiny, 2 times 10 to the power of minus 15. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So less than that tiny number. 16, isn't it, actually? Right. Which suggests our sample is inconsistent with there being no relationship between body weight and heart girth. So our conclusion would be that there is a relationship. Okay. What about the R squared value, this thing here? So what's this R squared? Well, we haven't talked about that yet. This is the proportion of variation in the outcome variable, which in this case is body weight, explained by the model, which in this case is heart girth. So what it's saying, that 0.8 or 80% of the variation in body weight is explained once we know what the heart girth is. Okay, so I'll talk about this a little bit more in lecture 7, but you can kind of see what's happening from this plot here, right? Before we know what heart girth is, the body weight could be anything between about 50 kilos and 225 kilos. So there's a huge range there of, say, 180 kilos or so, which the body weight could be. But once we know the heart girth, the plausible ranges for body weight reduce somewhat, right? So if we know the heart girth is, say, 100 kilos, then the range, maybe it's from 75 to 105 or so. So it's only sort of 30 kilos maybe 35 kilos is the range. Okay, the spread of potential body weights given we know the heart girth is 100. So somehow that big spread from 50 to 220 has been reduced to small spread from, say, 75 to 105. So we've explained variation, right? Most of the variation body weight comes due to the heart girth, right? As you vary the heart girth, you get variation in body weight. Body weight goes up. Okay, so by knowing what the heart girth is, you explain away a bunch of the possible variation in body weight and are only left with a little bit left over. So that's what's happening here. We've explained 80% of the variation in body weight once we know what the heart girth is. So the larger the multiple R squared is, the more you explain in your model. Okay, so the highest it could possibly be is 1, where all of the points would lie along a straight line. Okay, now the next thing we need to do is do a prediction. Right, so what would the body weight be if the heart girth is 110 centimeters? We can use the equation for this, right? Body weight would be minus 194.5 plus 2.83 times 110. Okay, so let's use RStudio for this. We can put it in, maybe we'll put a new code block here. All right. Now remember, times in R is the little asterisk above the 8. So let's run that. There we go, 16.8 kilos. Okay, so there we go. Okay, you could use your calculator for that as well, right? Or just, you know, do it by hand if you like as well. Okay, now we can do that same prediction using RStudio. Okay, so the predict function does that. Okay, this one here. And for the predict function, the predict function takes in our model, which we've called LM1, right? Back up here when we created our model with LM, we called it LM1. So that's the first parameter to predict. And the second parameter is a set of new data that you want to create predictions for. So the new data set that you need to do for predictions needs to have the same columns in it that your model has in it, right? So in this case, our model has heart girth in it, so we need a heart girth column. And then you can give it any values that you want. So here I've given it the value 110, right? So if I run that line, I'll get a new data frame called new data. It just has one row in it where the heart girth is equal to 110. Okay, I could add more rows if I want more predictions. So say I wanted it 120 as well, I could put 120 in another row. Okay, and then the predict function runs and gives us our answer. So there it is, the 116.68, which is pretty similar to what we computed by hand. Obviously this one's computed without any rounding, right? We had interim rounding here where we rounded the slope and the intercept. So that's why it's slightly different. Okay. So yay, this is similar to what we got from the equation. Difference is due to rounding. Okay. Now the problem with this prediction is that it's the prediction assuming that the equation here, that these numbers here are exactly correct. Okay, but we know they're not, right? It's from a sample. They have some error associated with them, with this, which is this next column here. So really what we want to do when we do our prediction is we want to do a prediction that incorporates the potential error in these estimates. Okay, and so that's what this next code block does. Okay, this first line here creates a confidence interval. Okay, gives us this answer here where we have the fitted value, which is 100, which is the same as we got from our predict, right? So that's our best guess at what the answer is, which is kind of assuming that these numbers are perfectly correct. But then we have a confidence interval. We have a lower possible value and an upper possible value, which is a 95% confidence interval for that value. Okay, so shows that if we have donkeys with heart girth 110 centimeters, then we're 95% confident that the mean body weight of such donkeys would be between 115.6 and 117.8 kilos. Okay, so essentially what we've done is we've incorporated the uncertainty in what the slope and the intercept are in that equation. Right, so the uncertainty in the equation, because the equation is generated from a sample of data and not the population. So this is the corresponding population mean for donkeys of heart girth 110 centimeters. Okay, but there's another source of variation in this data, right, which is the variation around the trend. So at the moment, we've essentially put a trend line through here. I'll show you how to do that in a moment. And we've described the uncertainty in the trend. So let's put the trend line on, perhaps, so that you can see it. What I'm going to do is I'm going to add on a geom smooth with method equals LM, which is short for linear model. I need the AES stuff so that it knows what's X and what's Y. There we go. Right, so you can see here that there's a grey band around this line. It's a little bit hard to see, isn't it? It's very, very tight here. That's the uncertainty in the line, okay? And that's the uncertainty that we've incorporated in our confidence interval. So it's just where the line is. So it's just the uncertainty about where the line is. It's not the variation around of the individual donkeys around the line, right? That's additional variation, okay? And so that's what the second line does, right? So the first line gives us the uncertainty in the location of the line. So that's the average, right? That's what the linear model is predicting. It's predicting the average. So that's what that confidence interval is. The second one here is the additional variation around the line of the individuals, right? So this is called a prediction interval. Adds on the variation around of individuals around the line. Right? Around the average. This is wider and is a 95% interval for individuals. i.e., so the interpretation would be we're 95% confident that individual donkeys would weigh, with heart girth 110 centimeters, would weigh between 95.4 kilos and 138 kilos. Okay, so that's a much broader range, right? Which makes sense. Yeah, we've got because we're doing a prediction for individual weight, and we know that individual donkeys differ quite a lot, right? Our model doesn't explain everything. It only explains 80% of the variation, right? So the location of the line explains 80% of the variation, but there's an additional 20% of the variation left over, which is incorporated into the variation of individuals about the average. Okay, so the confidence interval is for the average, just like the confidence interval for a mean is for the mean, right? It's for the population mean. It's not for the individuals in the population. It's for the average in the population. The population, a confidence interval for the prevalence is the average across the population, right? So the average is the proportion positive. So confidence intervals are for averages. Prediction intervals are for individuals. Okay. Right. And to finish off, we're going to look at the other variables in the data. So let's have a look at fitting some linear models for other ones. So what we're going to do is we'll do some plots first so that we can see what they look like. So x is going to be equal to, say, the length. Y is equal to the body weight. Right. So there's that. And then we're going to do a linear model. So we'll call it LM length. Body weight in terms of length. We'll do a summary of that. Okay. And maybe just for fun, we'll put the line on the plot as well. Okay, and here's the summary information. Okay, so let's write down the equations. The equation from this model. So for length, the equation is body weight equals minus 118.8 plus 2.94 times length. This model explains around 58% of the variation in body weight. Right, so the R squared is 58%, so it's less, isn't it? And you can see that makes sense because if you look at the plot, there's more scatter, right? So there's more additional variation in the individuals around the line, right? So our prediction intervals will be wider. Okay, so this will be length. Okay, now we'll just copy that code block and we'll do the other ones. So we'll do height. We'll call this LM height. You can call it whatever you like, right? It's just a name. Okay, so again, there's quite a lot of scatter around this line, so we'd expect the R squared to be a bit lower, and it's 61%. Okay, so the equation is going to be body weight is equal to minus 189.9, so minus 190 plus 3 times height. This model explains around 61% of the variation in body weight. So height's a little bit better than length is. Okay, and what about umbilical girth? Let's do that one as well. So we're going to go girth. Let's run that one. Okay, so again, there's lots of scatter around here. And you can see that actually maybe the straight line trend isn't working here quite so well because there's more scatter above the line than below it. Okay, so that suggests that you know, the model fit through here is pretty bad for these ones up here. Okay, we only explain 57% of the variation. So again, we can write down what the equation is. So body weight is equal to minus 101.1 plus 1.7 times umbilical girth. And this model explains around 57% of the variation in body weight. So you can see, you know, clearly that the heart girth one was the best, right? And you can see that from the plots, right? And this is just sort of confirmed by the R squared of the model. Now, just one thing to note about R squared is it only makes sense if it's a straight line relationship. So if you don't have a straight line relationship, then the R squared is not a good measure. Okay, so that's just something to watch for. So always plot the data first. If it's a straight line, then fitting a linear model makes sense, and your R squared will make sense. If it's not a straight line, then you might have to do something first. So you might have to perhaps do a transformation or something in order to transform the variables you have so that a straight line does make sense. Okay, and so we might see an example of that later on.